A fiery cosmic birth is being recreated on an ordinary workbench. This is the revolutionary world of tabletop analogues, where scientists build miniature universes in the lab to understand our own. By the end, you will see how a vat of superfluid helium can reveal the secrets of the Big Bang. We will uncover how cosmic strings might form like cracks in ice, and why the vacuum of space might not be empty at all. What does our entire cosmic history look like when you can hold a piece of it in your hands? That first cosmic moment was a cauldron of almost unimaginable energy. For a fleeting instant after the Big Bang, the universe was not filled with stars or planets, not even with atoms. It was a seething, swirling ocean of raw ingredients, a state physicists call the primordial soup. In this extreme environment, temperatures soared beyond trillions of degrees, a heat so intense that the fundamental building blocks of reality were torn apart. Protons and neutrons, the very heart of atoms, could not exist. Instead, their constituent parts, quarks and gluons, roamed freely in a frenzied plasma. This is the quark-gluon plasma, the universe's most fundamental soup. During these first microseconds, the forces that govern our reality were also indistinguishable from one another. The electromagnetic force and the weak nuclear force were merged into a single, unified electroweak force. It was a period of profound symmetry, a simplicity that would soon be lost. Cosmologist Alan Gough's theory of inflation suggests the universe underwent an incredible, exponential expansion in this era, smoothing out its texture and setting the stage for everything to come. Understanding this primordial soup is the key to understanding our own existence, why there is matter at all, and how structure eventually emerged. Yet, the energy scales of that time are so far beyond our reach that we cannot recreate them directly, not even with our most powerful particle colliders. This fundamental limitation forces us to get creative, to find another path back to the beginning. We are left with the challenge of a universe born in fire, a state we cannot physically recreate. Yet the human desire to understand is not so easily defeated. This is where the concept of an analog universe comes into play, a brilliant workaround that turns a profound limitation into a creative triumph. Think of a ripple tank, a simple classroom device where waves travel across the surface of water. By studying the patterns of these ripples, we can understand the fundamental principles that govern ocean waves, all without ever leaving the lab. Tabletop analogues apply this same logic to the cosmos. They use one physical system, something we can control and observe, to simulate the behavior of another system that is completely beyond our reach, like the infant universe. The history of science is filled with such analog simulations. For centuries, engineers have used water channels to model airflow over wings, and scientists have used sound waves in air to understand the properties of acoustics. Now, physicists are applying this established wisdom to the deepest mysteries of cosmology. Pioneers like Ulf Leonhardt demonstrated this power by using light traveling through specially designed materials to simulate the gravitational pull of a black hole, creating an optical analog that reveals insights we could never gather from the real thing. The magic lies not in recreating the immense energy of the Big Bang, but in identifying a shared mathematical blueprint. The equations that describe how sound moves through a fluid can look remarkably similar to the equations that describe how spacetime expands in the cosmos. The underlying physics is different, but the governing mathematics is universal. By building a tabletop experiment that masters the fluid system, we are, in effect, running a simulation of the cosmic system. We are bridging the immense gap between the very large and the very small, between the cosmos and the lab bench, by speaking the common language of mathematics. This allows us to hold a piece of cosmic history in our hands, not literally, but in a way that is just as revealing. So we arrive at a vat of superfluid helium, a liquid so strange it defies our everyday experience. It is a fluid with zero viscosity, meaning it can flow without any friction whatsoever. If you were to set it spinning in a beaker, it would, in theory, spin forever. But something remarkable happens when you rapidly stir this superfluid. As it cools through its transition point, it does not remain perfectly smooth. Instead, tiny whirlpools called quantized vortices spontaneously erupt throughout the liquid. These are not random swirls. They are defects in the otherwise perfect, ordered state of the superfluid. And in their formation, physicists see a stunningly accurate replay of the universe's own turbulent infancy. This is the power of an analog. The superfluid helium is not the primordial cosmos, but it behaves according to the same mathematical rules that govern the universe's first phase transitions. Think of water freezing into ice. As the temperature drops, the symmetric, freely moving water molecules must suddenly lock into a rigid, crystalline structure. But this transition does not happen perfectly everywhere at once. Different regions of the water freeze independently, and when their growing crystalline fronts meet, they often do not align perfectly. The result is a crack or a grain boundary in the ice, a defect in the perfect lattice. The early universe underwent a very similar process, but on a cosmic scale. As it expanded and cooled, the fundamental forces froze out from their unified, symmetric state into the distinct forces we know today. This cosmic freezing, this breaking of symmetry, is believed to have created its own kind of cracks in the fabric of spacetime. These are topological defects, with cosmic strings being one of the most fascinating possibilities. Imagine incredibly thin, unimaginably dense filaments of pure energy, thinner than a proton but stretching across the cosmos, each one a relic of a universal phase transition that occurred in the first fraction of a second. The question is, how do these defects form? The answer lies in a powerful idea called the Kibble-Jacques mechanism, proposed by physicist Tom Kibble and later refined by Wojciech. The theory is elegant. When a system undergoes a rapid phase change, it cannot communicate the change fast enough across its entire expanse. Information about the new, broken symmetry state can only travel at a finite speed. One part of the universe chooses one way to break symmetry, while a part just beyond its communication horizon chooses another. Where these different domains eventually meet, their incompatible choices become locked in, creating a topological defect. It is like trying to assemble a giant mosaic in the dark, with thousands of people working on their own small section. When the lights come on, you see that the tiles do not match up at the boundaries. Those mismatched seams are your defects. This is precisely what superfluid helium allows us to test. By quickly cooling the helium and stirring it, we force it through a rapid phase transition. We can then count the vortices that form. Their number, their distribution, they are a direct test of the Kibble-Jacques prediction. As Tom Kibble himself emphasized, without these laboratory tests, the theory of cosmic defect formation would remain pure speculation. The superfluid gives us a slow-motion, hands-on version of a process that was instantaneous and invisible in the early cosmos. By studying the whirlpools in a vat of helium, we are effectively reading the fingerprints of the universe's own structural birth. The formation of cosmic defects is just one piece of the puzzle. Another, even more profound event occurred in that first fleeting moment, an exponential stretching of space itself known as cosmic inflation. While we cannot witness its aftermath in a vat of helium, we can recreate its essence within an entirely different tabletop universe. Take a cloud of rubidium atoms and cool it to a temperature just a whisper above absolute zero, the point where all thermal motion nearly ceases. The individual atoms lose their identity, collapsing into a single, coherent quantum state known as a Bose-Einstein Condensate. This entire cloud of millions of atoms begins to behave not as a collection of particles, but as one giant quantum wave, a single entity. The collective behavior of the atoms in this condensate can be mathematically mapped directly onto the equations that describe the inflationary field, the mysterious energy that drove the universe's violent initial growth. In this analogy, the expansion of the atomic cloud itself becomes a simulation for the expansion of the cosmos. Scientists can precisely manipulate this expansion, tuning it to mimic different inflationary scenarios. As the condensate expands, tiny quantum fluctuations, which are always present at the subatomic level, get stretched and frozen into the fabric of the simulated spacetime. These are the primordial density fluctuations, the seeds from which all cosmic structure would eventually grow. Every galaxy, every star, every planet we see today originated from these minute variations, these quantum whispers amplified to a cosmic roar by inflation. Through the lens of a Bose-Einstein condensate, we can watch this process unfold in real time. We can test how different expansion rates affect the pattern of these fluctuations, comparing the results to the cosmic microwave background, the afterglow of the Big Bang. As physicist Stephen L. Adler has pointed out, these experiments bring the quantum origins of the universe's vast tapestry into the laboratory, transforming one of cosmology's most pivotal yet speculative chapters into a tangible, testable phenomenon. We are no longer just calculating what might have happened. We are observing a direct analog of the process that set the blueprint for everything. Light itself can become a miniature cosmos. Within the complex structure of a photonic crystal, a material engineered to control the flow of light, physicists build pathways that photons must follow, much like space itself dictates the motion of celestial bodies. When intense laser pulses are fired into certain nonlinear optical materials, their behavior transforms. The material's properties change in response to the light's own intensity, creating a dynamic environment where the path of a photon can bend and twist as if it were moving through curved spacetime. This setup becomes a direct analog for the quantum vacuum of the early universe, that seething sea of potential from which everything emerged. In the true vacuum of space, according to quantum theory, nothing is ever truly empty. It is a frothing ocean of virtual particles, pairs of matter and antimatter that constantly flicker into and out of existence. Under the immense gravitational fields of the early cosmos, or near a black hole, these fluctuations can be ripped apart, becoming real particles. This is the essence of phenomena like the Schwinger effect, where a powerful electric field can pull real particle pairs from the void, and Hawking radiation, where a black hole slowly evaporates by creating particles at its event horizon. These are monumental processes, but observing them directly in space is nearly impossible, lost in a fog of cosmic background noise. Yet, inside a nonlinear crystal, we can create a clean, controllable version of this very event. A powerful laser pulse can create an optical horizon, a point of no return for light within the material. Just as at the edge of a black hole, this artificial horizon can stimulate the creation of photon pairs from the quantum fluctuations of the crystal's own analog vacuum. We are not creating real black holes on a tabletop, but we are recreating the precise mathematical conditions that lead to Hawking radiation. We can watch it happen, measure it, and test its properties. As pioneering physicist John Pendry has articulated regarding metamaterials, The power lies in designing structures that offer a new perspective on old equations, giving us a master key to unlock nature's secrets. These optical experiments provide a pristine laboratory, free from the interference of the real cosmos, where we can directly witness the quantum field effects that likely shaped the universe in its first moments. We are using the behavior of light in a crystal to answer one of the most profound questions: how something can emerge from nothing, and watching as the ghostly whispers of the quantum vacuum are amplified into a signal we can finally see. A river can flow so swiftly that its current outpaces sound itself. This is the startling principle behind a sonic black hole, a phenomenon where a fluid moves faster than the waves traveling within it. Just as a gravitational black hole has an event horizon from which light cannot escape, a sonic black hole creates a point of no return for sound. If a sound wave is generated on the wrong side of this sonic horizon, it is dragged backward by the current, unable to ever make forward progress and reach an outside observer. This elegant analogy provides a stunningly direct path to studying one of the most elusive predictions in modern physics: Hawking radiation. In a landmark experiment, physicist Jeff Steinhauer used a Bose-Einstein condensate to create precisely this kind of flowing superfluid. By establishing a sharp transition where the fluid flow jumped from slower than sound to faster than sound, he crafted an analog event horizon. The magic happens because the quantum vacuum is never truly empty, not even in this tabletop fluid. Pairs of virtual sound waves, analogues to particle and antiparticle pairs, constantly flicker into existence at the horizon. The incredible flow of the fluid then rips these partners apart. One wave, representing the analog of a particle, gets swept away by the current, falling irretrievably into the sonic black hole. Its partner, however, is ejected outward, escaping as a real, detectable sound wave. This is the fluid equivalent of Hawking radiation, the very process by which real black holes are theorized to slowly leak energy and evaporate. For decades, this was a purely theoretical idea, impossible to verify near an actual black hole in space. But in the controlled quiet of the lab, Steinhauer and others could measure the properties of this emitted radiation. The results showed a thermal spectrum, a hallmark of true Hawking radiation, exactly as Stephen Hawking's equations had predicted. The mathematics governing the behavior of sound waves fighting a current in a fluid is formally identical to the mathematics describing light waves fighting gravity near a black hole's event horizon. This mathematical equivalence is the engine of discovery. It means that by listening carefully to the faint whispers of sound emanating from a fluid experiment, we are, in effect, eavesdropping on the quantum mechanics of a black hole. These sonic horizons offer a clean, reproducible window into the violent conditions of the early universe, a time when microscopic black holes may have been commonplace and the fabric of space-time was a turbulent sea of forming and evaporating horizons. We are not just simulating the cosmos, we are recreating its most extreme physics in a form we can finally measure, bringing the distant, ferocious birth of reality into the calm and precise world of the laboratory. A perfectly round, symmetrical ball of molten material holds every possibility within it. As it cools and crystallizes, its perfect symmetry is spontaneously broken. It must choose one specific geometric pattern, one alignment for its internal structure, locking into a beautiful but particular form. This is the essence of spontaneous symmetry breaking, and it is the very same process that forged the fundamental character of our universe as it cooled from its initial, featureless fire. In that primordial state, all the forces were one and particles raced at the speed of light, massless and free. But as the cosmos expanded and chilled, it underwent a series of cosmic crystallizations. The first and most profound of these was the Electroweak phase transition. where the unified electroweak force split into the distinct electromagnetic and weak nuclear forces we know today. This breaking of symmetry did more than just separate forces, it gave substance to the universe. It activated what we now call the Higgs mechanism. Imagine a crowded room where everyone is moving about freely. This is the early, symmetric universe. Then a famous person enters. The crowd spontaneously clusters around this individual. Moving through the room becomes more difficult. It requires more effort. In this analogy, the clustering crowd is the Higgs field, and the increased effort to move is what we perceive as mass. The Higgs field permeates all of space, and as particles interact with it, they acquire their mass, slowing from light speed to the slower paces that allow them to form atoms, planets, and us. This was not a theoretical abstraction, it was a physical event, a phase transition that swept across the infant cosmos. We can see a simpler version of this in a ferromagnet. When heated, its atoms jumble randomly, and it has no preferred direction. It is perfectly symmetric. But as it cools below a specific temperature, its atomic magnets spontaneously snap into alignment, choosing a north and south pole. The symmetry of the hot state is broken, giving the magnet a specific identity. Nobel laureate Peter Higgs's work helped reveal how this very process, on a cosmic scale, was responsible for endowing the universe with tangible structure. Without this breaking of symmetry, there would be no mass, no atoms, no stars. But the story does not end there. This same process of symmetry breaking may hold the key to one of the universe's greatest mysteries, why we exist at all. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter, which would have promptly annihilated each other, leaving behind a sea of pure light. The fact that we live in a universe dominated by matter means that this perfect symmetry was somehow broken. A slight preference for matter over antimatter must have been baked into the laws of physics during one of these early phase transitions. Perhaps during the Electroweak transition or another even earlier breaking, certain processes behaved differently for matter and antimatter, resulting in a tiny 1 in a billion excess of matter. That minuscule surplus is everything. It is the leftover material that formed every galaxy and every living thing. By studying how symmetries break in controlled laboratory settings, in superfluid helium and Bose-Einstein condensates, we are reverse engineering the sequence of cosmic events. We watch order emerge from chaos and see how a system chooses one path from many perfect possibilities. Each experiment is a replay of a critical moment, revealing the hidden order behind the apparent randomness of our complex cosmos, showing us how a universe of pure potential became a universe of tangible, beautiful reality. These cosmic cracks are not just theoretical curiosities, they are potential fossils. The universe's rapid cooling could have frozen imperfections into the very fabric of space-time, relics known as topological defects. Picture the formation of ice once more. As water freezes, different regions form crystals with random orientations. Where these misaligned crystals meet, a flaw is trapped in the structure, a permanent crack or grain boundary. The early universe underwent a similar but far more fundamental freezing process. As it expanded and cooled, the underlying fields that govern reality settled into new, more stable states. But this settling did not happen uniformly. Distant regions, unable to communicate, chose different vacuum states, different ways to break the universe's initial symmetry. Where these conflicting domains met, their mismatched configurations became locked in, creating persistent structures. The most famous of these are cosmic strings, hypothetical filaments of pure energy thinner than a proton, but with the mass of a mountain range per inch, potentially stretching across the entire cosmos. Other defects could exist too, like domain walls, vast two-dimensional sheets that would separate regions of space with different physical properties. These are not made of matter, but are kinks and wrinkles in the very fields that fill the vacuum. Grand unified theories which attempt to merge the electromagnetic, weak, and strong nuclear forces predict that such defects would have been copiously produced in the universe's first moments. Finding one would be like discovering the preserved blueprint of a cosmic phase transition, a direct snapshot of physics at energies we can never hope to recreate in a collider. But how can we be sure such bizarre entities are even possible? This is where the laboratory bench becomes a time machine. Scientists use systems like liquid crystals, the same materials in your watch display, to watch defects form in real time. A liquid crystal can flow like a liquid, but its molecules have a certain order like a crystal. When you heat it and then cool it rapidly, it undergoes a phase transition. As it cools, different domains form with molecules pointing in different directions. Where these domains collide, you see dark lines appear under a microscope. These are topological defects in the liquid crystal, direct analogues to cosmic strings and domain walls. They are the Kibble-Zsuk mechanism made visible. The theory proposed by Tom Kibble and refined by Wojciech states that the density of these defects depends on the speed of the transition. A rapid quench leaves little time for coordination, resulting in a messy, defect-riddled outcome. A slow, careful cooling allows the system to align smoothly. Researchers can precisely control the cooling rate in a vat of superfluid helium or a sample of liquid crystals and count the resulting defects. The numbers match the theoretical predictions with stunning accuracy. This laboratory evidence is crucial. It tells us that if the early universe cooled in a certain way, which our best models say it did, then these cosmic fossils must have formed. The hunt for them in the cosmos continues through their subtle gravitational effects on light or their potential imprint on the cosmic microwave background. But even without a direct astronomical discovery, the tabletop experiments have already given us profound confidence. They bridge the immense gap between the abstract mathematics of particle physics and the tangible history of cosmology, showing us how the universe's broken symmetries are written not only in equations, but potentially in the very architecture of spacetime. We can now program the universe's first moments. Picture a perfect three-dimensional grid of light, a lattice created by crisscrossing laser beams. At each point of intersection, a single atom is held perfectly suspended, isolated and chilled to almost absolute zero. This is an optical lattice, and it functions as a quantum simulator, a device that uses one controllable quantum system to mimic the behavior of another that is impossibly complex to calculate. Here, the individual atoms become stand-ins for the fundamental quantum fields that filled the infant cosmos. By adjusting the lasers and magnetic fields, physicists can precisely tune how these atoms interact with one another, effectively reprogramming the very rules of their simulated universe. This allows them to recreate conditions akin to the quark-hadron transition, the moment when the free-roaming quarks and gluons of the primordial soup first locked together to form protons and neutrons. They can even map the complex phase diagram of quantum chromodynamics, the theory that governs the strong nuclear force. This diagram is like a cosmic map of states of matter, showing how quarks behave under different temperatures and pressures. As physicist Emanuel Bloch has explained, these simulators offer an unprecedented level of control over quantum many-body systems. We are no longer passive observers of the cosmos, we have become active participants. We can ask what would have happened if the fundamental constants were slightly different. What if the strong force was a bit weaker or the quark mass was altered? By tweaking the parameters in the optical lattice, We can run these cosmic what-if scenarios directly on the lab bench. We watch as the simulated system either forms stable matter or collapses into something entirely alien, testing the robustness of our cosmological models with a precision that was once the realm of pure fantasy. This is not merely observation, it is experimentation on the laws of creation themselves, conducted with atoms in a light-filled crystal. Even the universe's most elusive ghosts can cast shadows in the lab. We have journeyed through the birth of forces and the formation of cosmic strings, but two vast mysteries remain: dark matter and dark energy. These invisible components are thought to make up 95% of the cosmos, yet they reveal themselves only through their gravitational pull on the motions of galaxies and the expansion of space itself. How can we possibly study something so intangible? The answer, once again, lies in the power of the analog. Picture a specially prepared superfluid, a quantum liquid flowing without friction. Within this fluid, scientists can create collective excitations, waves, and ripples that move through the entire system. The behavior of these waves can be precisely mapped onto the equations that describe a leading candidate for dark matter, known as fuzzy dark matter. This theory proposes that dark matter is not made of discrete particles, but is an ultra-light scalar field, a kind of invisible mist permeating all of space. In the superfluid analog, the waves act like the ripples in this cosmic mist. Under the right conditions, these ripples can collapse into stable, self-reenancing waves called solitons. A soliton is a wave packet that holds its shape as it travels, like a single, persistent hum moving through the fluid. In the context of the dark matter analog, these solitons are behaving like the dense cores of dark matter that theorists believe sit at the centers of galaxies. We are not creating dark matter itself, but we are recreating its proposed dynamics in a system we can control and observe. This gives us a sandbox to test how this form of dark matter would clump and interact, how it would shape the formation of galactic halos. The connection can stretch even further into speculative realms. Some theories, explored by physicists like Lisa Randall, suggest that the effects we attribute to dark matter could arise from gravity leaking into extra-spatial dimensions. While we cannot build a higher dimensional space in the lab, certain complex fluid systems can be engineered to exhibit mathematical behaviors that mimic these proposed geometries. We are building functional stand-ins for the cosmos's deepest architecture. These experiments are not direct detections, but they are crucial testing grounds. They allow us to explore the nonlinear, complex dynamics of dark sector candidates, moving beyond simple equations to see how these hypothetical entities actually behave in a real, physical system. For dark energy, the mysterious force accelerating cosmic expansion, similar analogues are being conceived. Could an expanding Bose-Einstein condensate be tuned to simulate not just the early inflation, but the late-time accelerated expansion we see today? The possibility is on the horizon. By holding these cosmic mysteries in a beaker, we transform them from abstract puzzles into tangible phenomena, offering a new path to understand the dark universe that surrounds us. A field, silent and invisible, permeates every cubic inch of the cosmos. This is the Higgs field, and its awakening was the moment the universe gained substance. As the cosmos cooled through a critical temperature in its first picosecond, it underwent the Electroweak phase transition. The unified Electroweak force split in two, and in that breaking of symmetry, the Higgs field shifted from a state of high symmetry to one of lower energy, much like supercooled water suddenly and explosively crystallizing into ice. This cosmic freezing did more than just release latent heat. It fundamentally altered the nature of reality. Particles that had previously raced at the speed of light, massless and free, began to interact with this newfound field. Some, like photons, passed through unaffected, remaining massless. Others, like the W and Z bosons and the quarks, found their passage hindered, as if moving through a persistent universal syrup. This resistance is what we perceive as mass. Without this event, there would be no atoms, no chemistry, no solid matter. The universe would be a formless sea of light-speed radiation. Yet this transition holds an even deeper secret, one that might explain our very existence. The Big Bang should have created equal amounts of matter and antimatter, a perfect symmetry that would have led to total annihilation. The fact that we are here means that symmetry was broken, resulting in a tiny 1 in a billion excess of matter. This process, called baryogenesis, might have been driven by the electroweak phase transition itself. As the Higgs field changed state, it could have created the precise conditions necessary for processes that treated matter and antimatter slightly differently, allowing a surplus of matter to survive. Testing this idea requires us to replay that cosmic moment, and tabletop analogues provide the stage. Consider a ferromagnet. When heated, its atomic magnets point in random directions, a state of perfect symmetry. But when it cools below the Curie point, it must choose a direction for its magnetic field, spontaneously breaking that symmetry. The dynamics of this transition, how bubbles of the new phase nucleate and expand, mirror the physics of the early universe. In certain superconductors, the behavior of magnetic flux lines as the material transitions can be mapped directly onto equations describing the Higgs field. As theorist Nima Arkani-Hamed has emphasized, the profound connection between particle physics and cosmology becomes tangible in such experiments. We are not merely calculating what might have happened, we are watching a scaled-down version of the process that gave the universe its fundamental properties. By tweaking parameters in these magnetic and superconducting systems, we can explore different baryogenesis scenarios. Was the transition sudden and violent, or smooth and gradual? The answer, written in the domain structures of a laboratory magnet, tells us how the cosmos crossed the threshold from a symmetrical, featureless fire into a structured, material world. A high-intensity laser pulse strikes a microscopic target, compressing it in an instant into a speck of matter hotter than the core of a star. This tiny, ultra-hot droplet is a quark-gluon plasma, the primordial soup of the early universe, recreated not over miles of tunnel but within a fraction of a millimeter. Massive colliders like the Large Hadron Collider smash heavy nuclei together to create this state, but they do so over a vast volume. Tabletop laser setups achieve a similar extreme density and temperature in a fundamentally different way, offering a complementary view into the universe's first moments. The laser-driven plasma is born from a violent, rapid-fire explosion, a far cry from the controlled collision of two ions. This difference in initial conditions is not a bug, it is a feature. It allows scientists to probe how the quark-gluon plasma thermalizes, how this frenzied soup of particles reaches a state of equilibrium. Does it happen instantly, or is there a chaotic scramble as quarks and gluons fight to establish order? The answer is written in the way this miniature fireball expands and cools. By analyzing its evolution, physicists can measure a critical property, its viscosity. How syrupy or how perfect a fluid was this primordial state? The laser-induced droplets suggest it was nearly a perfect fluid, flowing with almost zero resistance, a characteristic that would have profoundly influenced how the first structures later condensed from the cosmic soup. Researchers in laser plasma physics describe the immense challenge of these experiments, of creating a stable, uniform plasma that lasts long enough to be measured. Yet their achievements are stunning, miniaturizing the most extreme conditions imaginable onto a laboratory workbench. These small-scale analogues provide a unique window into the strongly coupled nature of the early universe's matter. where interactions are so intense that individual particles lose their identity to the collective whole. We are not just recreating the soup, we are learning to stir it, to test its fundamental properties in a new and powerful way, bringing the fluid dynamics of the cosmos itself into sharp, tangible focus. Even empty space, the deepest vacuum we can conceive, is not truly empty. It hums with a faint, persistent energy, a force inherent to the fabric of reality itself. This is vacuum energy, and its most famous manifestation is the cosmological constant, the mysterious driver of our universe's accelerating expansion. The problem is its magnitude. The calculated energy of empty space is a staggering 120 orders of magnitude larger than what we observe, a discrepancy so vast it is the worst prediction in the history of physics. To tackle this puzzle, we are now building universes with different rules on a tabletop, using the strange world of metamaterials. These are not naturally occurring substances, but are intricately engineered structures, often with repeating patterns smaller than the wavelength of light. By designing their geometry, we can grant them electromagnetic properties impossible in nature, such as a negative refractive index, where light bends in the opposite direction from what we expect. In such a custom-built material, the way light propagates is no longer described by the simple vacuum of space, but by a new set of effective rules. The equations governing its path become mathematically identical to those describing a universe with a specific cosmological constant. We are not creating new universes, but we are creating materials that perfectly mimic their space-time geometry. By tuning the metamaterials design, we can effectively dial in different values for this constant, creating an analog cosmos where the vacuum energy is stronger, weaker, or even negative. We can then watch how light, or even sound waves in acoustic metamaterials, behaves as it travels through this artificial space-time. Does it experience an effective acceleration, stretching out as if space itself were expanding? We can observe it directly. More profoundly, we can probe how the quantum vacuum behaves in these altered settings. The ever-present quantum fluctuations, the virtual particles that flicker at the edge of existence, are the source of the vacuum energy problem. In a metamaterial with a tailored cosmological constant, we can study how these fluctuations respond. Do they amplify, or do they suppress one another? Experiments have begun to test these very questions, sending photons through these engineered structures and measuring subtle changes in their behavior that reveal the properties of the simulated vacuum. This gives us an empirical handle on a problem that was once purely theoretical. Theorist Leonard Suskind's concept of the string theory landscape provides a grand context for this work, suggesting a vast multiverse where each universe has its own unique vacuum energy, its own cosmological constant. We just happen to inhabit one where the value is curiously small and life-permitting. The metamaterial experiments offer a tiny, accessible corner of this landscape. They allow us to ask what the cosmos would look like if the vacuum energy were different. Would structure ever form? Would galaxies ever coalesce? By building these custom-tailored realities, we move from passive observation of our single universe to active exploration of cosmic possibility, testing the boundaries of physical law from the quiet confines of the laboratory. A spinning vat of liquid metal becomes a crucible for cosmic creation. Within a sealed, spinning container, liquid sodium churns in a violent, turbulent dance. This is not an industrial process, but a deliberate attempt to recreate the conditions that gave birth to the universe's first magnetic fields. The entire cosmos is threaded with magnetism, from the delicate spiral arms of galaxies to the vast voids between them. These fields are fundamental to cosmic structure, influencing how stars form and how matter collapses into galaxies. yet their origin is one of cosmology's great unsolved puzzles. How did a universe born in a hot, neutral plasma, a state with no inherent magnetic fields, become so thoroughly magnetized? The answer appears to lie in a powerful engine known as the dynamo effect. In a conducting fluid like liquid sodium or the primordial plasma, any tiny, initial magnetic seed, perhaps a random fluctuation, can be stretched, twisted, and amplified by the fluid's motion. It is a self-reinforcing cycle where the motion of the conductor generates electrical currents, which in turn strengthen the magnetic field, which then further influences the flow. The challenge is that the infant universe was a maelstrom, a place of such intense turbulence that the mathematics becomes nearly impossible to solve. This is where the laboratory provides a crucial shortcut. Experiments like the von Karman sodium apparatus force liquid sodium between two counter-rotating impellers, generating a controlled, fully measurable version of that primordial chaos. Researchers can watch as the chaotic flow, given just a tiny magnetic nudge, spontaneously organizes and amplifies a powerful, large-scale magnetic field right before their eyes. As plasma astrophysicist Fausto Cattaneo has noted, these experiments reveal the universal thresholds for dynamo action, the specific conditions of turbulence and conductivity that must be met for a magnetic field to grow. The liquid sodium is a direct stand-in for the early universe's plasma, allowing us to test different theories of magnetogenesis. Was the initial seed field provided by the subtle density fluctuations from inflation, or did it arise later from the violent shocks of the first cosmic structures? The lab dynamo does not create the seed, but it shows us exactly how such a seed, whatever its origin, could be amplified from a quantum whisper into a cosmic force that shapes galaxies. By mastering the turbulent flows in a spinning container of metal, we are effectively tracing the lineage of the magnetic fields that now weave through the fabric of space itself, watching the invisible engine of the cosmos roar to life on a workbench. The quantum jitters of the newborn cosmos were stretched into the blueprint for reality. During inflation, the universe did not simply expand. It exploded in size, magnifying the faintest quantum tremors in the inflationary field into vast hills and valleys of density. These primordial perturbations, these fossilized quantum fluctuations, became the gravitational seeds for every galaxy cluster and cosmic void we see today. The process is deeply quantum, yet its echo can be found in the classical flow of water. In a laboratory water tank, researchers can generate a controlled, flowing current. They then introduce a tiny, regular disturbance, a gentle, consistent vibration that sends a train of small ripples across the water's surface. As these ripples travel into a region where the flow suddenly accelerates, like over a small weir or through a constriction, something remarkable happens. The ripples are stretched and amplified, their wavelength growing and their energy increasing as the water's flow carries them forward. This is a direct classical analog to the amplification of quantum fluctuations during cosmic inflation. The mathematical mapping is the key that unlocks this cosmic secret. In the equations, the velocity potential of the fluid, which describes the energy of its flow, plays the role of the inflationary field. The small density fluctuations in the water, the ripples and waves, are the stand-ins for the quantum perturbations in that field. The sudden change in the fluid's flow speed acts as the analog for the exponential expansion of spacetime. By carefully measuring how the initial vibrations are transformed into larger waves, physicists can test the fundamental mechanisms of perturbation growth. This fluid dynamics approach offers a stunningly intuitive window into a process governed by quantum mechanics. We can watch with our own eyes how a uniform input of tiny disturbances can, through the right kind of stretching, produce a complex spectrum of larger waves, a power spectrum that can be directly compared to the one imprinted on the cosmic microwave background. The work of cosmologists like Andre Linde, who explored the concept of eternal inflation and a vast multiverse where different regions undergo different inflationary histories, finds a curious parallel in the unpredictable outcomes of turbulent fluid flows. In a chaotic water channel, small differences in initial conditions can lead to wildly different final wave patterns, a classical hint at the profound diversity that may be possible on a cosmic scale. Observing a ripple grow in a tank gives us a tangible, classical intuition for the quantum mechanical lottery that determined the fate of our entire visible universe, a process whose signature is written across the sky. The greatest asymmetry in the cosmos is the one that made us possible. For every billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. That minuscule surplus, that 1 in a billion imbalance, is the only reason anything made of atoms exists today. The puzzle of how this happened is called Baryogenesis, and its solution requires 3 specific ingredients, known as the Sakharov conditions. As physicist Helen Quinn has explained, the universe needed to undergo processes that violated baryon number conservation, that operated outside of thermal equilibrium, and that treated matter and antimatter differently. This last condition is known as CP violation, where C stands for charge and P for parity. It means the laws of physics must show a slight but definitive preference for matter over antimatter. Finding evidence of this violation in new contexts is where tabletop science enters the stage. One of the most sensitive searches looks for a property called a permanent electric dipole moment in fundamental particles like the electron or neutron. Imagine a perfectly spherical particle. If it has an even distribution of charge, its center of positive and negative charge overlap perfectly, and it possesses no dipole moment. But if CP violation is at work, this perfect symmetry could be ever so slightly broken. The particle might be ever so slightly egg-shaped, with a tiny, permanent separation of charge, like a microscopic battery. Detecting this would be a monumental discovery, a direct signal of new physics that favors matter. The incredible precision required for this measurement is achieved not in miles-long colliders, but in compact, exquisitely controlled experiments that trap and observe individual atoms or neutrons for remarkably long times. In these quiet, small-scale labs, scientists can probe for a wobble in a particle's spin that would betray that telltale asymmetry. The sensitivity is so great they are testing energy scales far beyond what the Large Hadron Collider can directly access. Beyond particle physics, the same principles can be explored in the condensed matter universe of quasi-particles. These are not fundamental particles, but collective excitations in a material that behave as if they were. In certain exotic crystals, these quasi-particles can be engineered to exhibit effective CP violation in their interactions. We are not creating antimatter in these systems, but we are creating a sandbox where the mathematical rules governing matter-antimatter asymmetry are in play. By observing how these quasi-particles behave and decay, we can test the robustness of the mechanisms that theorists propose could have tipped the cosmic scales. No tabletop experiment can recreate the entire fiery process of baryogenesis, but each one acts as a forensic tool, examining the fundamental building blocks of that primordial event. They test whether nature's laws contain the necessary subtle biases, providing crucial experimental constraints that guide our theories. Every time a measurement of a particle's shape comes back null, it tells us what the universe is not, narrowing the path toward understanding the 1 in a billion fluke that allowed our material world to be. The vibrations of spacetime itself are now echoing through solid metal and sand. Gravitational waves, the ripples predicted by Einstein, carry the memory of cosmic cataclysms, from colliding black holes to the universe's own violent birth. Observing them directly with instruments like LIGO was a triumph, but their extreme faintness makes studying their fundamental nature a monumental challenge. This is where the laboratory bench offers a powerful alternative, using sound and vibration to build a functional model of these space-time tremors. In a solid block of metal, sound waves are not so different from gravitational waves. Both are transverse waves, meaning they oscillate perpendicular to their direction of travel, and both can be described by similar sets of equations. This mathematical kinship allows physicists to use a vibrating metal bar as a direct analog for a gravitational wave detector. Just as a real gravitational wave would stretch and compress space-time as it passes, a sound wave of the right frequency can set a metal bar resonating, stretching and compressing it in a measurable way. Researchers can then probe how these simulated waves interact with each other and with the medium itself, testing the nonlinear dynamics that are thought to have been dominant when the universe was a seething, high-energy arena. The exploration goes even further with specially designed granular materials, collections of tiny particles like fine sand. In such a material, the way vibrations travel from one grain to another can be engineered to mimic the specific polarizations of gravitational waves, the distinct patterns in which they distort space. As Nobel laureate Kip Thorne has articulated, understanding these polarizations is key to unlocking the nature of the cosmic events that created them. These tabletop experiments allow scientists to generate and control these polarization states directly, observing their behavior in a controlled setting. Certain mechanical metamaterials, with their repeating, engineered structures, can be designed so that their collective oscillations obey equations that are formally identical to those of general relativity in a confined space. This creates a miniature universe where the laws of gravity are encoded in the physics of sound. In this analog cosmos, scientists can send vibrations through the material and watch how they scatter, bend, and interact, effectively running experiments on the nonlinear behavior of gravity itself. We are not creating real gravitational waves on a tabletop, but we are creating their precise mathematical shadow. By listening to the resonant hum of a metal bar or tracing a vibration through a bed of sand, we gain a tangible, intuitive grasp of the forces that shape the cosmos from its very first instant. A black hole's surface area might hold the key to the universe's deepest nature. When physicists studied the thermodynamics of black holes, they made a startling discovery. The maximum amount of information a black hole can contain is not proportional to its volume, as you might expect, but to the area of its event horizon. This bizarre fact gave rise to the holographic principle, a radical proposal that all the information describing our three-dimensional reality could be encoded on a two-dimensional surface, much like a hologram on a credit card stores a three-dimensional image. Our universe, with all its stars, planets, and people, might in fact be a vast and incredibly complex projection from a thin, distant shell. For decades, this was a breathtaking but entirely theoretical idea, seemingly impossible to test. But then a remarkable connection emerged, not in deep space but on a lab bench. Certain materials, like sheets of graphene or exotic superconductors, exhibit electronic behaviors that are mathematically identical to a universe obeying the holographic principle. The frenzied dance of electrons across a two-dimensional surface in these materials can be perfectly described by equations that also govern particles moving through a higher dimensional space that includes gravity. This is the essence of the AD-S/CFT correspondence, a duality first proposed by string theorist Juan Maldacena. Maldaceno's work revealed a profound equivalence, a gravitational theory in an anti-de Sitter space, a type of universe with a negative cosmological constant, is completely equivalent to a conformal field theory, a quantum theory without gravity, living on its boundary. One system with gravity is dual to another system without it. This means that by studying the quantum physics of electrons on a flat, two-dimensional chip, we are, in a very real mathematical sense, probing the properties of a hypothetical gravitational universe. We are building the hologram and studying the projected image simultaneously. As Maldacena himself has noted, this duality provides a unique way to understand quantum gravity, turning an abstract philosophical puzzle into a concrete problem in quantum mechanics. In the lab, researchers can measure how heat and electrical charge flow through these special materials. These measurements translate directly into calculations about how black holes in the dual gravitational theory absorb and emit information. We are not creating tiny black holes, but we are creating systems that share their underlying mathematical blueprint. Each experiment on electron transport becomes a test of the holographic principle's predictions, offering a tangible pathway to explore whether our own reality is fundamentally a lower dimensional information structure. The cosmos becomes a grand projection, and on a workbench we hold the projector in our hands. Our universe's first moment remains its most profound secret. This is the Planck epoch, a fleeting span of time so short it defies imagination, where the energy was so concentrated that the very concepts of space and time as we know them break down. In this primordial regime, gravity was not a smooth classical force, but a frenzied quantum phenomenon, intertwined with all the other forces. We have no complete theory to describe this unity of quantum mechanics and general relativity, making it the final frontier of fundamental physics. Yet, even here, in a domain seemingly forever beyond direct observation, tabletop analogues are carving a path forward. By using exquisitely controlled quantum systems, physicists are building working models of hypothetical quantum spacetime. In a Bose-Einstein condensate, for instance, the collective behavior of atoms can be manipulated to behave as if they are quantum fields propagating on a curved, dynamic background. The subtle interactions between atoms can mimic how particles might move and interact on a geometry that is itself fluctuating, giving us a glimpse into how matter and spacetime could have co-evolved from the very beginning. Other proposals are even more radical, suggesting that optical networks of interfering laser beams could simulate spin foam models. These are theoretical frameworks where spacetime is not smooth and continuous, but is instead composed of tiny, discrete loops and volumes, a frothing sea of quantum connections. In such an experiment, the pathways of light through the network would represent the evolution of these fundamental spacetime quanta. The ultimate goal, as quantum gravity pioneer Carlo Rovelli has articulated, is to find a coherent theory that seamlessly blends the probabilistic world of the quantum with the geometric fabric of relativity. These laboratory experiments do not provide that full theory, but they offer something equally vital: empirical data. They allow us to test the behavioral consequences of different quantum gravity models. We can ask, if spacetime is fundamentally discrete, how would that discreteness affect the propagation of light or sound in our analog system? We can observe how quantum correlations emerge and evolve in a simulated gravitational context. Each measurement is a clue, a piece of a puzzle that guides theorists away from mathematical dead ends and toward a more complete picture of cosmic birth. We are building toy universes that obey the speculative rules of quantum gravity, not to prove they are real, but to learn what their reality would actually look and behave like, bringing the universe's very first whisper of existence into the realm of experimental science. A universe 1 second old was a seething, opaque fog. Within this primordial glare, neutrinos reigned supreme. These ghostly particles, so ethereal that trillions pass through your body every second without a trace, were not always so aloof. In the first instance, the cosmos was so unimaginably dense that even neutrinos, which rarely interact with anything, were trapped. They slammed into protons, neutrons, and electrons, acting as a dominant pressure that shaped the universe's expansion and influenced how the first atomic nuclei forged in the furnace of Big Bang nucleosynthesis. This cosmic neutrino background is a direct relic from that first second, a fossil snapshot almost as profound as the cosmic microwave background. Today, these neutrinos stream through space, cooled to just a few degrees above absolute zero, yet their collective gravity subtly guides the formation of galaxies and the vast cosmic web. We cannot detect these ancient neutrinos directly, for they have lost almost all their energy. So how do we possibly study a particle that is both everywhere and seemingly nowhere? The answer lies in a different kind of laboratory, one that measures the ghosts of the present to understand the architects of the past. Deep underground, in caverns shielded from cosmic rays, experiments like Camland and Daya Bay perform a kind of particle alchemy. They do not recreate the early universe, but they perform a crucial complementary task. By capturing neutrinos emitted from nuclear reactors or the sun, they measure with exquisite precision how these particles oscillate, spontaneously changing from one type or flavor to another as they travel. This bizarre phenomenon is only possible if neutrinos have mass, a finding that overturned the long-standing standard model of particle physics. Nobel laureate Arthur B. MacDonald, who led the Sudbury Neutrino Observatory, articulated this profound link, stating that the properties of neutrinos studied in these deep laboratories are essential for interpreting the universe's evolution. Each precise measurement of a neutrino's mass or its oscillation probability acts as a boundary condition for our cosmological models. When we run simulations of the universe's first 3 minutes, the period of nucleosynthesis, the number of neutrino types and their properties determine how much hydrogen and helium was created. The data from our underground labs tells the simulation what rules to follow. If neutrinos were massless as once thought, or had different interaction strengths, the resulting elemental abundances would not match what we observe in the oldest stars. By pinning down the behavior of these shadow particles here and now, we are effectively constraining the thermal history of the entire cosmos. We are using the subtle quirks of a particle we can barely catch to read the fine print of the universe's birth certificate, connecting the infinitesimal to the infinite. That faint cosmic static on an old television set holds the universe's oldest photograph. The cosmic microwave background is the cooled remnant of the Big Bang's fireball, a snapshot of the cosmos when it was just 380,000 years old. In this image, we see the seeds of all future structure, tiny variations in temperature that map the density fluctuations from which galaxies would eventually grow. These temperature spots form what is known as a Gaussian random field, a specific statistical pattern where the fluctuations are random but follow a predictable bell curve distribution. This pattern is a key prediction of the simplest models of cosmic inflation. But what if there are subtle deviations from this perfect randomness, tiny twists in the pattern known as non-Gaussianities? Finding them would be like discovering a hidden signature in the cosmic blueprint, a clue pointing to more complex physics during the universe's explosive birth. To learn how to spot these subtle signatures, we are creating similar blueprints right here on Earth. A metal plate vibrated by a speaker becomes a chaotic sea of ripples. The pattern of peaks and troughs on its surface is not a perfect replica of the cosmic microwave background, but it shares the same underlying mathematical structure. It is a Gaussian random field in 2 dimensions. By studying this vibrating plate, physicists can test the tools and statistics they use on the actual sky map. They can learn how to distinguish true signals from mere background noise. This principle extends to other chaotic systems, like the speckle pattern created when a laser beam reflects off a rough surface. The seemingly random pattern of bright and dark spots is another example of a Gaussian field. As cosmologist John M. Kovac, whose work helped map the CMB's polarization, has emphasized, understanding the statistics of these random fields is paramount. It is the difference between simply seeing the static and learning to read the message hidden within it. In the lab, we can introduce controlled imperfections into these analog systems, creating known non-Gaussian signatures. We can then see how our statistical tools perform in detecting them. It is a training ground for cosmology, allowing us to refine our methods on a system we fully control before applying them to the universe's own ancient photograph. By mastering the statistics of a speckle pattern or a vibrating plate, we are sharpening our vision, preparing to decode the faintest whispers of new physics from the first light of the cosmos. Our universe might be a single bubble in a cosmic foam of realities. This is the multiverse hypothesis, a speculative but profound idea suggesting that our entire cosmic history, from the Big Bang to the present, is just one possibility among a potentially infinite number of other universes, each with its own unique physical laws. It is a concept that seems forever beyond the reach of direct experiment, a playground for theoretical physicists and philosophers. Yet, even here, on the quiet laboratory bench, we find powerful metaphors that bring this staggering possibility into sharper focus. Consider a simple parametrically driven oscillator, a pendulum whose pivot point is jiggled up and down at a precise frequency. This seemingly mundane system does not have just one stable state of motion. Instead, it possesses a landscape of possible states. It can swing to the left or it can swing to the right with equal stability. The system must choose one of these two realities, these two low-energy configurations, even though the fundamental driving force is the same. This is a direct miniature analog for the string theory landscape. In string theory, the fundamental equations may allow for a vast number of possible solutions, perhaps 10 to the 500 or more, each one corresponding to a universe with different constants, different particles, and different forces. Our universe, with its specific values for the strength of gravity and the mass of the electron, would then be just one point in this colossal landscape of possibilities, one stable swinging state among countless others. The laboratory oscillator does not create an alternate universe, but it demonstrates a core principle that a single underlying theory can give rise to a breathtaking diversity of low-energy physics. This metaphorical connection helps physicists visualize and reason about eternal inflation, the theory that the inflationary expansion of space may be a perpetual process, continually spawning new bubble universes. Each bubble could be a different point in the landscape, crystallizing with its own random set of physical laws. As multiverse proponent Max Tegmark has suggested, this forces us to confront deep philosophical challenges like the measure problem. If an infinite number of universes exist, how do we calculate the probability that we would find ourselves in one like ours? The laboratory systems provide a sandbox for exploring such questions of probability and selection on a manageable scale. By studying how a driven system chooses its state from a menu of options, we gain an intuitive grasp of how our entire cosmos might be just one accidental outcome in a much grander reality. These experiments are not proof of the multiverse, but they transform it from a purely abstract speculation into a conceptual framework that can be probed, at least indirectly, through the shared language of mathematical behavior. A fundamental rule of quantum mechanics states that information can never be truly destroyed. It can be scrambled beyond recognition, but the complete blueprint of what fell into a system must, in principle, be recoverable. This principle of unitarity is the bedrock of our understanding of the quantum world. Yet, a black hole presents a terrifying challenge to this rule. When matter and energy cross the event horizon, they seem to vanish from our universe, taking their information with them. If the black hole then evaporates through Hawking radiation, which is thermal and featureless, that information appears to be permanently erased. This is the black hole information paradox, a profound conflict between general relativity and quantum mechanics that has puzzled physicists for decades. The very foundations of physics seem to fracture at the singularity. But what if we could recreate this paradox in a controlled environment, not with gravity, but with sound? This is the power of an analog black hole in a Bose-Einstein condensate. By establishing a sonic event horizon, a point where the fluid flows faster than the speed of sound, we create a point of no return for phonons, the quantum particles of sound. Just as with a real black hole, pairs of virtual phonons are ripped apart at this horizon. One partner falls inward, past the point of retrieval, while the other escapes as detectable Hawking radiation. For a long time, the focus was solely on detecting this outgoing radiation, which was a triumph in itself. But the real key to the information paradox lies not in the radiation alone, but in the subtle, invisible connection between the two partners. These particles are quantum entangled, their fates intertwined no matter how far apart they are separated. The escaping Hawking phonon and its infalling twin are linked by a quantum thread. If information is to be preserved, it must be encoded in the correlations between all the pairs of Hawking particles emitted over the black hole's lifetime. The information that seemingly fell in is not lost, but is instead imprinted onto the radiation in a complex, scrambled form. Researchers are now designing intricate experiments to detect these specific correlations. By carefully probing the quantum noise just outside the sonic horizon, they can search for the statistical signature that confirms the entangled partners exist. Finding this correlation would be a monumental step, a strong hint that information is, in fact, preserved in the process of evaporation. As quantum information theorist Seth Lloyd has pointed out, these experiments shift the question from whether information is lost to how it is transferred and encoded. The analog system provides a pristine laboratory to study the unitarity of quantum evolution in a setting that mimics a gravitational collapse. While a sonic black hole is not a gravitational one, the mathematical equivalence is so precise that any discovery about information flow in the analog informs the debate about our real cosmos. These tabletop experiments do not yet resolve the grand paradox, but they provide our first experimental handle on a problem that was once purely philosophical. They allow us to watch information teeter on the edge of oblivion and perhaps begin to understand how it finds a way to escape. A chemical reaction inside a perfectly stirred beaker can only produce life's building blocks within an exquisitely narrow window of temperature and pressure. Slightly too hot or too cold, and the delicate dance of molecules fails, yielding only inert sludge. This phenomenon, where a specific, complex outcome depends on a precise set of initial conditions, is a form of fine-tuning we can witness and manipulate in the laboratory. It serves as a powerful conceptual mirror for one of cosmology's most profound puzzles, the apparent fine-tuning of our universe's own fundamental constants. The force of gravity, the strength of the nuclear forces, the mass of the electron, each of these values seems to be set with incredible precision. If any one of them were even slightly different, atoms would not be stable, stars would not ignite, and life as we know it would be impossible. This observation leads directly to the anthropic principle, idea articulated by physicist Brandon Carter. In its simplest form, the principle suggests that the universe we observe must be compatible with the existence of observers. We should not be surprised to find the constants finely tuned for life, because if they were not, we would not be here to notice. The laboratory gives us a controlled environment to explore this logic. Consider running an evolutionary algorithm on a computer, a digital world where virtual creatures compete for resources. The programmer sets the rules, the parameters for survival and reproduction. You quickly discover that complex, intelligent behavior only emerges within a very specific range of these parameters. Tweak them just a little, and the simulation either collapses into chaos or stagnates in simplicity. This is not proof of the anthropic principle in the cosmos, but it is a stark illustration of how selection effects operate. In the digital world, you only see the interesting, complex outcomes from the tiny fraction of parameter space that allows them. The vast majority of settings produce nothing noteworthy at all. This laboratory perspective fuels a deep philosophical debate. Does the apparent fine-tuning of our universe point toward a deeper, fundamental theory that necessarily produces these values? Or does it suggest our cosmos is just one among a vast multiverse, a single bubble in a cosmic froth where every possible set of constants is realized somewhere? In this multiverse picture, we simply find ourselves in one of the rare, life-permitting bubbles, a cosmic version of the lucky parameter setting in your computer simulation. By studying fine-tuning in chemical baths and digital worlds, we gain a tangible framework for contemplating a question that traces back to the universe's first moments. Are the laws of physics a unique, inevitable truth, or are they a contingent, almost accidental, set of rules that just happen to allow for stars, planets, and us? These tabletop analogues do not answer the question, but they give us a vocabulary and a set of tools to think about it, transforming a metaphysical mystery into a subject we can hold, measure, and explore. Quantum simulators are already beginning to rewrite cosmic history, one atom at a time. In the coming decade, these tabletop universes will evolve from simulating single events to modeling entire cosmic sagas. Imagine a single optical lattice, its grid of trapped atoms acting as a programmable quantum field. Researchers will not just trigger a phase transition, they will choreograph the entire sequence, from the inflationary burst and the subsequent reheating that repopulated the universe with particles, to the final formation of hadrons. This non-equilibrium dance, the violent transition from an empty, inflated space to a hot, particle-filled cosmos, is a chaotic process that supercomputers struggle to calculate. A next-generation quantum simulator could run it in real time, revealing how the first matter actually condensed from the primordial energy fields. Beyond atomic systems, two-dimensional materials like graphene offer a stunning new canvas. The exotic electronic behavior in these atomically thin sheets can be mathematically mapped onto particles moving through curved spacetimes with properties impossible in our universe. We could effectively engineer a cosmic geometry where the speed of light varies with direction, or where dimensionality itself is an emergent property, testing the limits of physical law. These advanced materials, combined with the raw processing power of quantum computing, will allow us to tackle phenomena that have remained purely theoretical. How did quantum fluctuations during inflation get converted into the particles we see today? What precise mechanisms violated the symmetry between matter and antimatter? To find the signals for these events in the vast data streams from these experiments, scientists are turning to machine learning. These algorithms will sift through the quantum noise, identifying subtle patterns and correlations that would be invisible to the human eye, uncovering the faint fingerprints of cosmic genesis. As one leading experimentalist noted, we are moving from simply observing analog phenomena to actively controlling them with a degree of precision that mirrors the universe's own deterministic laws. The workbench of the future will not just hold a piece of cosmic history, it will contain a dynamic, evolving model of creation itself, offering our most tangible path to answering the ultimate question of how something as complex as our universe could have emerged from almost nothing. We are now architects of Genesis, building pocket universes that obey our command. This power to recreate cosmic birth in a laboratory carries a profound weight of responsibility, raising ethical and philosophical questions that echo as deeply as the science itself. When we manipulate the fundamental processes of reality, even in analog form, we are playing with the very rules of existence. The primary ethical concern, while distant, revolves around the potential to create stable, exotic states of matter. Could an experiment designed to mimic a cosmic phenomenon accidentally produce a self-sustaining entity or a phase of matter with unpredictable properties? The consensus in the scientific community is that the energy scales involved make such a risk infinitesimally small, especially compared to the natural, high-energy particle collisions occurring constantly in our atmosphere. Yet, this very remoteness is why rigorous oversight and international collaboration are not just bureaucratic hurdles, but essential safeguards. They are the embodiment of the precautionary principle, ensuring our curiosity is always tempered by wisdom. This cautious approach is rooted in a long tradition of scientific philosophy. Karl Popper argued that for a theory to be truly scientific, it must be falsifiable, capable of being proven wrong through experiment. Our tabletop universes are the ultimate expression of this principle. They take the grand, untestable narratives of cosmology and subject them to the harsh, clarifying light of laboratory falsification. But they also force us to confront the limits of our knowledge. Can a simulation ever truly capture the entirety of the real thing, or are we merely seeing a shadow of a deeper truth? The very act of creation in the lab challenges our understanding of causality and determinism. If we can press a button and initiate a process that perfectly mirrors the birth of cosmic structure, what does that say about the randomness of our own universe's beginning? Was it also the inevitable outcome of a set of physical laws, a determined script written at the dawn of time? Or does our ability to start the process over and over, with slightly different parameters each time, suggest a cosmos of profound contingency, where our existence hinges on a series of fragile, accidental outcomes? These are not just abstract puzzles, they strike at the heart of our place in the cosmos. Are we accidental tourists in a vast, indifferent machine, or are we the universe itself becoming conscious, using its own laws to look back and understand its own origins? Engaging with these implications is not a diversion from science, it is an essential part of the journey. It ensures that our relentless pursuit of knowledge remains thoughtful, humble, and grounded, reminding us that as we unravel the mysteries of existence, we are also redefining our relationship with reality itself. A single equation can travel from a laboratory notebook to the edge of a black hole. This is the incredible journey of discovery that defines modern cosmology, a continuous loop where tabletop experiments and astronomical observations constantly inform and refine one another. The superfluid helium experiment, with its whirlpools and vortices, provides a powerful example. When physicists count the number of defects formed during a rapid quench, they are testing the Kibble-Juk mechanism, a theory that predicts how many cosmic strings should have formed in the early universe. The laboratory data gives cosmologists a crucial number, a predicted density for these hypothetical filaments. This number then directly influences the design of telescopes and the analysis of sky maps. Astronomers searching for the subtle gravitational lensing effects of a cosmic string now know what to look for. What density of strings would confirm the theory or rule it out? The tabletop result has set a target for the entire field. Similarly, the faint glow of Hawking radiation measured in a flowing Bose-Einstein condensate has profound implications for how we interpret data from gravitational wave observatories. The thermal spectrum observed in the lab provides an expected signature, a template for what the evaporation of a real black hole might look like, even if we cannot directly detect its radiation yet. It tells theorists that the underlying quantum process is sound, guiding their models of how black holes evolve and merge. This creates a powerful synergy. A cosmologist wrestling with a puzzling feature in the cosmic microwave background can turn to a condensed matter physicist and ask, "Can you build a system that produces this kind of pattern?" The lab becomes a testing ground for exotic cosmological models, a place to run controlled what-if scenarios that the universe itself only performed once. This collaboration is dismantling the old barriers between the science of the impossibly large and the science of the incredibly small. It reveals a profound truth that the same physical principles govern the formation of a vortex in liquid helium and the birth of a galaxy. By mastering the intricate details of a quantum fluid on a workbench, we gain the master key to decipher the architecture of the cosmos itself. The universe is not two separate realms, it is one continuous reality, and we are now learning to read its story from both ends at once. A high school student might build a sonic black hole from a sink and a speaker, hearing the point where sound itself cannot escape. This is the transformative power of tabletop cosmology in public engagement. These experiments transform abstract, intimidating concepts into something you can see, hear, and even touch. A simple cloud chamber, built with dry ice and alcohol, reveals the constant, ghostly dance of particles being created from the vacuum, a direct echo of the early universe's frenetic energy. When a student sees that ethereal trail with their own eyes, the quantum world shifts from a set of confusing equations to a tangible, buzzing reality. Science communicator Neil deGrasse Tyson often speaks of this visceral connection, noting that the moment a complex idea clicks into place is a moment of genuine magic, one that can ignite a lifelong passion for discovery. By bringing the cosmos down from the distant heavens and onto the workbench, we demystify the entire scientific endeavor. Public demonstrations of superfluid vortices or laser-based analogues make it clear that the laws governing black holes and the Big Bang are not mystical decrees, but physical principles that can be explored and tested. This accessibility is crucial. It builds a bridge between the esoteric world of theoretical physics and the public's innate curiosity about our origins. When people can witness a simulation of cosmic inflation in a vibrating water tank, they gain an intuitive understanding that no lecture could ever provide. This shared wonder does more than just educate, it inspires. It plants a seed in a young mind that might one day design the next great experiment or solve the mystery of dark energy. It fosters a society that values and supports the fundamental research that pushes the boundaries of human knowledge, ensuring that the profound question of our cosmic beginnings continues to be asked and answered for generations to come. Our journey began in the furnace of the Big Bang and has led us here to the quiet hum of a laboratory bench. These tabletop analogues offer a brilliant detour around a fundamental limitation, providing a tangible window into cosmic epochs we can never visit directly. They allow us to test the very laws that forged reality, from the violent birth of space-time defects to the quantum whispers that seeded all galactic structure. The profound revelation is the stunning universality of physics itself. The same mathematical principles that describe whirlpools in superfluid helium govern the formation of cosmic strings, and the collective dance of atoms in a Bose-Einstein condensate can replay the inflationary expansion of the entire cosmos. This is not merely simulation, it is a deep exploration of the shared blueprint underlying all of nature. Every one of these experiments stands as a monument to human curiosity, a daring attempt to hold a piece of cosmic genesis in our hands and comprehend our own origins. Let this new perspective fill you with wonder the next time you look at the night sky. The universe is not distant and untouchable. Its deepest secrets are being unraveled right here in labs across the planet. We would love to hear what astonished you most on this journey. Share your thoughts and questions below, and let's keep this conversation about our cosmic beginnings alive.